When structures fail, they fail violently. A snapping steel cable instantly detonates millions of joules of stored energy into the surrounding air. That violent release is the physical manifestation of strain energy. It is mechanical work that has been absorbed and conserved within a deformable body. This technical illustration of an urban environment demonstrates how physical infrastructure functions as a giant mechanical battery. Up to a precise threshold known as the elastic limit, structural elements like these glowing bridge cables absorb external forces and store them as recoverable potential energy. That same energy storage happens deep underground. Geotechnical foundations and retaining walls constantly absorb massive kinetic shock waves from the surrounding earth, banking that energy as shear strain. Structural survival relies on a strict capacity to absorb physical work without yielding. This infographic maps the architecture of that stored energy. The capacity of our mechanical battery is patterned by 4 universal parameters. We must account for the rate of loading, the effective volume, the physical material moduli, and the multi-axial dimensionality of the applied stress. Preventing a collapse requires predicting the exact mathematical threshold where this mechanical battery exceeds its limits and ruptures. Plotting applied load against extension, the large triangular area calculates the total stored strain energy, defined as resilience. The peak of that triangle marks the elastic limit. Energy stored exactly at this boundary is proof resilience, the maximum capacity the material safely holds. Cross that specific threshold and the battery breaks. The material undergoes permanent plastic deformation, and its original shape is lost. To compare different materials, engineers use the formula block shown here to calculate the modulus of resilience. We define this by dividing the proof resilience by the total volume of the body, yielding the formula sigma squared over 2e. Yield strength only tells you how much static force a material resists. The modulus of resilience determines its true capacity to absorb dynamic physical shocks. This diagram illustrates a gradually applied load. As a weight is slowly lowered, the force increases linearly, creating a triangular work area. The mechanical work equals the area of that triangle, 1/2 the load P times the extension delta, providing a safe static stress baseline. But the time domain dictates everything. We must calculate what happens when that exact same load is transferred instantaneously. This comparative graphic illustrates the 2x phenomenon. Under sudden loading, the full weight P remains constant throughout the entire deformation process, making the work area a full rectangle. Equating this to stored strain energy yields a severe penalty. Internal stress exactly double the static baseline. When forces become entirely dynamic, we encounter impact loading, a mass falling freely from a defined height before striking a structure. Kinetic energy from the fall forces the metallic crystalline lattice to compress and warp, demanding it instantly absorb the shockwave without fracturing. This impact loading diagram maps the necessary energy balance. The potential energy of the falling weight must equal the total strain energy stored. Expanding this relationship produces a quadratic equation, isolating an exponential impact shock factor multiplier, driven almost entirely by the falling height h. This details a critical engineering shortcut. In macrostructures, instantaneous elongation is infinitesimally small compared to the drop height. Dropping the elongation variable simplifies the quadratic into a square root equation, isolating a direct relationship between drop height, material volume, and stress. A stationary mass safely rests on a column. That exact same mass, applied suddenly, will yield it. Dropped from a height, it will shatter it entirely. The rate of kinetic transfer governs the physical outcome. This matrix summarizes our axial parameters, mapping how the time of application scales internal stress from a safe baseline to an exponential penalty. This shear stress diagram shows how energy is stored through angular deformation. Instead of elongating, the structural block warps under uniform shear stress, accumulating energy inside the deformed volume. The mathematics remain perfectly symmetrical. The shear energy equation mirrors the axial formula, simply swapping Young's modulus for the material's modulus of rigidity. This vertical dynamics diagram visualizes self-weight. Massive vertical structures act as uneven accumulators, forced to absorb the mechanical strain of their own gravity. Because internal forces compound continuously from top to bottom, calculating the total stored energy requires integrating the stress along the column's entire vertical length. For discrete, stepped sections used in heavy construction, that integral becomes a scalar sum. Engineers calculate the individual energies stored in each segment and add them together. This bending beam diagram visualizes flexural energy. Bending induces a complex internal gradient, placing the top in compression while stretching the bottom in tension. To calculate total flexural strain energy, we use the integral approach, integrating squared bending moment over the beam's flexural rigidity. In heavy industrial power systems, drive shafts like this store vast amounts of rotational energy, derived from intense twisting moments integrated across the cylindrical volume. In highly dynamic environments, such as this leaf spring suspension, engineers stack materials specifically to integrate these bending and shear energies, safely absorbing repetitive vehicular impact. Whether a force twists, shears, or bends a material, the mathematical architecture of the mechanical battery remains entirely symmetrical and predictable. When engineers miscalculate these integrated stress limits, or real-world kinetic events overwhelm the math, the mechanical battery fails. This historical photograph of severely buckled railway tracks illustrates a massive release of uncontained strain energy. Static yield strength determines the point of initial deformation, but structural survival is defined by the total volume of energy the system can absorb. It's a dynamic equilibrium, governed by this energy architecture schematic. We define our battery by securing the right effective volume and material moduli, then cross-reference those against the dimensionality of stress and the unforgiving rate of loading. Overcharge the battery beyond its proof resilience, and the material violently returns the energy it can no longer safely hold. By mastering the precise mathematics of strain energy, structural engineers ensure the physical world's kinetic environment standing.